Good morning, everyone. Thank you for joining us. I'm Will Ramey, Director of Developer Programs here at NVIDIA. Over the next hour, I'm going to share a high-level, lightly technical introduction to some powerful data science techniques, including deep learning, that will help you understand what is accelerated data science, what deep learning is good for, and why it's such a powerful technology, how deep neural networks are trained, optimized, and deployed in applications, and the challenges many organizations face when first getting started with deep learning. At the end, we'll wrap up with some recommendations to help you get started using deep learning in your own applications. We have a team of NVIDIA solution architects and engineers helping me answer your questions in the chat console, so ask away. Data science is a broad field that covers everything related to data cleansing, preparation, and analysis. It involves statistics, mathematics, programming, and creative problem solving to extract information from data. When GPU acceleration is used to improve the performance of data science workflows with accelerated data science. Data analytics, machine learning, and deep learning are widely used approaches to solving problems in the field of data science. Data analytics has been around for a long time. It's used to examine sets in order to draw conclusions about the information they contain using correlation, statistical modeling, and other methods. Machine learning uses statistics techniques to construct a model from observed data. It generally relies on human-defined classifiers or feature extractors that can be as simple as a linear regression or the slightly more complicated bag of words technique that made spam filters possible. This was really handy in the late 1980s when lots of uninvited emails started showing up in your inbox, and it continues to be a popular approach to solving many data science challenges. Then we invented smartphones, webcams, social media services, and all kinds of sensors that generate huge mountains of data, and the new challenge of identifying the many features in that data and the correlations between them that actually matter. Deep learning is a machine learning technique that automates the creation of these feature extractors, a process we call feature engineering. It uses large amounts of data to train complex, deep neural networks. Deep neural networks are capable of achieving human-level accuracy for many tasks, but require tremendous amounts of computational power to train. Several years ago, researchers started applying deep neural networks in a variety of areas and reporting amazing results. We'll dig deeper into deep learning in a few minutes, but first, let's take a look at how deep learning fits into the broader context of GPU-accelerated data science with a few examples. Many companies, organizations, and even governments are realizing that accelerated data science can help them be more efficient and more effective. Here, you can see a partial list of the industries and use cases where GPU-accelerated data science can have a big impact. In healthcare, for example, accelerated data science can be used to better predict disease drivers with genomic medicine, improve health outcomes with analysis of electronic medical records, and predictively determine the best care or treatment for a wide range of health conditions. Energy and utilities companies can use accelerated data science to optimize energy distribution in smart grids and reduce outages with predictive maintenance. Microsoft's Skype Translator performs installation of conversations to and from over 60 languages. If you haven't tried this yet, it's a really amazing way to connect and communicate with people across language barriers. Enterprises large and small can use accelerated data science to analyze customer data for new product development, monitor the security of their IT systems and physical facilities, and implement reports that reveal deeper insights for business decision makers. How do you know which approach to data science will work best for the problems you're trying to solve? The answer often lies in the types and the quantity of data you have to work with. If the problem you're working on is well-defined or straightforward enough that you don't need machine learning or deep learning, then more direct analytics methods like XGBoost, PageRank, similarity analysis, or single source shortest path can deliver good results with minimal effort. If you're working on these types of projects, I highly recommend checking out the Rapids open source platform, which provides accelerated implementations of many data science algorithms. If you need a more sophisticated approach, your data is organized into a table or sparsely populated data structure, and you know what the important features are, then machine learning techniques, questions, and decision trees will generally work well. And if you have a big collection of images, videos, audio recordings, log files, or other dense data, and don't know or have time to figure out what the important characteristics or features are, deep learning is likely a good approach. Often, the best solution is a combination of multiple approaches, with the output of one feeding into the next until you achieve the desired result. And regardless of the approach you take, the amount of data that needs to be processed is only increasing. McKinsey recently estimated that over 2 exabytes of data are created each day, and research firm IDC reports that big data and business analytics will generate over $260 billion annually by 2022. In fact, 90% of the data in the world today was generated in just the last 2 years. It turns out that deep learning is stunningly effective across many domains, and it's transforming the way computers achieve perceptual tasks such as computer vision, pattern detection, speech recognition, and behavior prediction. Some observers, including Bloomberg and the World Economic Forum, have referred to it as the fourth industrial revolution. And Andrew Ng, a widely respected Stanford University professor, co-founder of the Google Brain Project, and co-founder of the Coursera online education platform, believes that deep learning is the new electricity, stating that just as 100 years ago, electricity transformed industry after industry, AI will now do the same. Many people want to know why and how deep learning is being adopted so rapidly. Well, there were 3 key ingredients, or you might think of them as initial conditions, that made the current big bang of modern AI possible. First was big data, the huge collections of examples from which computers can learn. Second, researchers needed to develop parallel algorithms that allow data scientists to design and train deep neural networks to process the big data. And third was the introduction of programmable GPU accelerators that make it possible for researchers to implement their algorithms on a flexible platform and complete the massive amounts of computation required in a practical amount of time. Early researchers published their algorithms and neural network models in research papers and scientific journals, but they also released the software they created, packaged up in high-level open source frameworks, so others could build on top of their work instead of starting from scratch. And all the major deep learning frameworks support GPU acceleration because it just wasn't practical to do this computationally intense work without GPUs. Cloud platform providers recognized the potential of deep learning to improve their own services and the business opportunity of offering GPU-accelerated deep learning platforms in the cloud. Now, all the major cloud service providers make GPUs available to their customers. This significantly reduced the capital costs and time investment for startups, which motivated a huge influx of venture funding for deep learning startups. In early 2017, there were about 1,000 AI startups and about $5 billion in funding to fuel them. Now, just a few years later, there are more than 12,000 startups with over $150 billion funding them. And research firm Tractica is projecting a $500 billion opportunity in the next 10 years. Large companies, governments, and other organizations, influenced by the impressive achievements of startups and researchers, are rapidly adopting this new technology, seeing it as a competitive advantage or a potential threat if they fail to effectively master it. It can be helpful to think about deep learning as a way to map data samples from an input domain to an output domain. The input domain can be text data, such as log files or financial data, images of pretty much anything, audio or other signals, or video streams, which are really just a sequence of images with synchronized audio. It can even be three-dimensional images or data sets collected from medical imaging devices, geophysical analyses, cosmological models, or molecular dynamics simulations. The output domain is determined by the question to ask of the input data, and the question itself indicates the type of deep learning task you need to perform in order to map the input domain to the output domain. This table shows a sampling of use cases where deep learning can be applied in healthcare, retail, and finance. For example, if the question requires a yes/no answer telling you whether something is present, the task is detection. If the question requires an answer describing what types of things are in each input, the task is classification. And if the question requires a shape or a volume as an answer, the task is segmentation, and so on. Depending on the application, you may need to use a combination of tasks to achieve more sophisticated outputs. For example, to automatically label all of the faces in your family photos, you'd need to first detect whether and where there are faces in the picture, and then apply facial recognition, which is a form of classification, to determine the name of the person associated with each face. And for language translation, you could use speech to text, a form of classification, followed by translation of text in one language to text in another language, a form of prediction, and then speech synthesis, which can also be implemented as a form of prediction. Different deep learning tasks require different models. Here, you can see a variety of representative deep neural network models that have been simplified to highlight their differences. Convolutional neural networks, or CNNs, are the workhorse for analyzing 2D and 3D images and video, including classification, prediction, and segmentation tasks. CNNs can also be used for grouped sequence data and regression problems like predicting a continuous variable, such as price, as a function of various factors. CNNs are also getting popular for some types of sequence analysis, for example, DeepMind's WaveNet voice synthesis. Recurrent neural networks, or RNNs, work really well on sequences, including many natural language processing tasks such as sentiment analysis, speech recognition, machine translation, handwriting and gesture recognition, and time series forecasting. Generative adversarial networks, or GANs, are actually two deep neural networks competing with each other to generate images or other results that are incredibly realistic. This technique has been used to create images of people, environments, shoes, clothing, or other products, as well as automatically constructing 3D models from 2D. GANs have also been used to perform image up-resolution, drug molecule design, and to generate many answers for the same question. Reinforcement learning is used to automatically determine the ideal behavior or decision within a specific context. Examples include optimizing resource management in computer clusters, teaching robots to perform complex tasks, and personalized recommendations. And new species of deep neural network models are emerging as researchers continue to explore new ideas and solve larger, more complicated problems. Let's take a look at how deep learning actually works in practice. Say you want to automatically identify various types of animals, which is a classification task. The first step is to assemble a collection of representative examples to be used as a training data set, which will serve as the experience from which a deep neural network will learn. If you only need to classify cats versus dogs, then you only need to have cat images and dog images in the training data set. In this case, you'll need several thousand images, each label indicating whether it is a cat image or a dog image. To ensure the training data set is representative of all the pictures of cats and dogs that exist in the world, it must include a wide range of species, poses, and environments in which cats and dogs may be observed. The next thing you need is a deep neural network model. Typically, this will be an untrained neural network designed to perform a general task like detection, classification, or segmentation on a specific type of input data like images, text, audio, or video. Here, you can see a very simple model of an untrained neural network. At the top of the model, there is a row or a layer that has 4 input nodes. And at the bottom, there's a layer that has 2 output nodes. Between the input layer and the output layer are a few so-called hidden layers with several nodes each. The white lines show which nodes in the input layer are shared with the nodes in the first hidden layer, and so on, all the way down to the output layer. You may hear the nodes referred to as artificial neurons or perceptrons, since their simple behavior is inspired by the neurons in the human brain. A real deep neural network model would have many hidden layers between the layer and the output layer, which is why it's called deep. But a simplified representation works fine for this example. Just keep in mind that the design of the neural network model is what makes it suitable for a particular task. For example, the best models for image classification are very different from the best models for speech recognition. And the differences can include the number of layers, the number of nodes in each layer, the algorithms performed in each node, and the connections between nodes. It's worth noting that there are readily available deep neural network models for image classification, object recognition, image segmentation, and several other tasks. But it's often necessary to modify these models to achieve high levels of accuracy for a particular data set. So, the computation required to train one version of the model is multiplied by the number of model variations that need to be evaluated. And all of this processing requires a tremendous amount of computation, much of which can be performed in parallel, which makes deep learning an ideal workload for GPUs to accelerate. So, if the goal is to train a deep neural network to distinguish cats versus dogs, you would use a neural network model that is designed to be good at image classification. Once you've assembled a training data set and selected a neural network model, a deep learning framework such as MXNet or TensorFlow or PyTorch is used to feed the training data set through the neural network. For each image that is processed through the neural network, each node in the output layer reports a number that indicates how confident it is that the image is a dog or a cat. In this case, there are only 2 options, so the model needs just 2 nodes in the output layer, one for dogs and one for cats. When these final outputs are sorted most confident to least confident, the result is called a confidence vector. The deep learning framework then looks at the label for the image to determine whether the neural network guessed or inferred the correct answer. If it inferred correctly, the framework strengthens the weights of the connections so that the connections that contributed to getting the correct answer. And vice versa, if the neural network inferred an incorrect result, the framework reduces the weights of the connections that contributed to getting the wrong answer. After processing the entire training data set once, the neural network will generally have enough experience to infer the correct answer a little more than half of the time, which is slightly better than a random coin toss. But it will require several additional epochs, meaning rounds of processing the entire training to achieve higher levels of accuracy. There are many deep learning frameworks to choose from, each with its own set of strengths, programming language interfaces, etc. But they're all GPU accelerated using the CUDA Deep Neural Networks library, or cuDNN, and other libraries in the NVIDIA Deep Learning SDK. You can learn more about all the deep learning frameworks and the NVIDIA Deep Learning SDK on our website at developer.nvidia.com. So, Now that the model has been trained on a large representative data set, it's very good at distinguishing between cats versus dogs. But if you showed it a picture of a raccoon, it would be very confused, since it has no previous experience with raccoons and would probably report a low confidence number for both dog and cat. If you actually needed the ability to classify raccoons as well as dogs and cats, you would simply modify the design topology of the model to add a third node to the output layer, expand the training data set to include thousands of representative images of raccoons, and use the deep learning framework to retrain the model. There's no need to manually write a raccoon feature extraction algorithm and figure out how to integrate it into your deep neural network model. You just modify the network topology a bit and retrain the model with your new data set. Once the model has been trained, much of the generalized flexibility that was necessary during the training process is no longer needed. So it's possible to optimize the model for significantly faster runtime performance. Common optimizations include fusing layers to reduce memory and communication overhead, pruning nodes that do not contribute significantly to the results, and other techniques supported in the NVIDIA TensorRT runtime. Your fully trained and optimized model is then ready to be integrated into an application that will feed it new data. In this case, images of cats and dogs that it hasn't seen before. And it will be able to quickly and accurately infer the correct answer based on its training. And your application can be deployed on a GPU-accelerated platform in your data center, in the cloud, on a local workstation, in a robot, a smart camera, or even a self-driving car. So let's switch gears and talk about a few challenges that many organization researchers might encounter when first adopting deep learning. The first is that this is a brand new computing model. Most data scientists, developers, and researchers don't have a lot of experience working with it yet. And to apply it effectively, you need to learn how to approach problems a little bit differently from a more data-centric perspective. Another challenge is that the algorithms used for deep learning continue to evolve and improve very rapidly. So keeping up with all the latest advances that may benefit your work can require significant time and effort. And as you saw earlier, training deep neural networks is tremendously computationally intensive. So you need to plan your projects to take advantage of high-performance computing platforms that can process large amounts of data quickly. A final challenge is that once you have a trained neural network, it's really flexible. You could deploy it in a cloud-based web service for low latency facial recognition or e-commerce recommendations, a powerful workstation for medical imaging diagnoses, a safe and reliable self-driving car, smart cameras for intelligent video analytics, and more. So you need a wide range of GPU-accelerated deployment platforms to benefit from this flexibility. Let's take a look at some of the things NVIDIA is doing to help you overcome these challenges. To address the first challenge and help data scientists and software engineers quickly ramp up on deep learning, the NVIDIA Deep Learning Institute offers hands-on training that gives you the experience you need to solve challenging problems using deep learning. The Deep Learning Institute, or DLI, delivers project-based hands-on training through online courses and on-site workshops presented by DLI-certified instructors. We do this by giving each student a GPU-accelerated deep learning development system in the cloud, so you can learn how to use all the latest open-source deep learning frameworks, tools, and more without having to set up your own system from scratch. All the major cloud service providers offer GPU-accelerated systems, so we just use some of them to deliver hands-on training that helps you get started quickly with deep learning from anywhere in the world. And of course, the training covers not only the image classification workflow that we talked about earlier today, but also application domains such as natural language processing, intelligent video analytics, healthcare, robotics, anomaly detection, predictive maintenance, self-driving cars, and more. We've announced several new courses recently, including one designed to help IT professionals learn how to deploy and manage AI workloads in the data center. So far, we've trained over 200,000 people worldwide and are scaling up to meet the increasing demand. One of the best places to learn everything you need to know about deep learning is NVIDIA's GPU Technology Conference, GTC. This year at the GTC in Silicon Valley, thousands of developers, researchers, and data scientists will join us to see the amazing work being done with AI and other GPU-accelerated technologies across a wide range of application domains. They'll meet the experts and innovators who are leading the rapid evolution of deep learning and learn how to apply this powerful technology to improve their own work. More than half of the 600-plus sessions this year will be focused on AI and deep learning. At the conference, you'll hear from experts representing a wide range of industries, as well as academic and government organizations sharing their work on applications in healthcare, automotive, finance, aerospace, defense, retail, manufacturing, and more. Key speakers come from NVIDIA, Google, Amazon, Microsoft, IBM, Adobe, Facebook, BMW, Toyota, Stanford, Oxford, University of Toronto, several national labs, and, well, I'll stop there, but the list goes on. GTC is really the only place where you can connect one-on-one with so many experts across so many industries. And the Deep Learning Institute is hosting several full-day workshops on Sunday before the conference, as well as presenting more than 60 hands-on training sessions throughout the week. The next GTC is here in Silicon Valley at the end of March. And to thank you for joining us today, I'm sharing my personal registration code that will save you 25% on GTC registration. Check out the website for special university, government, and nonprofit rates. And be sure to register for the Conference Plus Training Pass so you can attend all the hands-on training sessions during the conference. A great resource for startups is Inception, NVIDIA's virtual accelerator program focused on supporting young AI companies with the resources they need at various stages of their journey. The focus of the Inception program is to help startups make technical and commercial progress on creating their product or service and building their business without requiring any equity in exchange. The three main benefits of the program are AI expertise via education from the Deep Learning Institute for startup teams and one-on-one guidance where appropriate from NVIDIA solution architects. Go-to-market support through co-marketing and joint sales programs with companies that are ready, and access to NVIDIA technology through early access to our software libraries and a discount program on hardware and a partnership with AWS that provides credits to startups building applications at scale. Our 5,000 plus members span with strong representation in the Americas, Europe, and Asia Pacific. Inception startups operate across industries ranging from AI platforms and tools to healthcare, to financial services, and even agriculture. We've seen more than 17x growth since Inception was launched in 2016. Our focus is on creating a global community that will deliver on the tremendous promise of AI. NVIDIA also invests heavily in software you can use to quickly take advantage of deep learning. Our dedicated engineering teams work closely with all the deep learning framework developers to ensure they have support for the latest GPU-accelerated algorithms via the NVIDIA Deep Learning SDK and CUDA. So regardless of which open source deep learning framework you choose to train your deep neural network models, you don't have to be a GPU programmer to take advantage of built-in support for GPU acceleration. We also provide deployment solutions for inference applications running in the cloud or data center, embedded platforms, and autonomous vehicles. And for developers who want to build their own deep learning capabilities from the ground up, the comprehensive NVIDIA Deep Learning SDK includes all the latest GPU-accelerated deep learning algorithms in the CUDA Deep Neural Network, or cuDNN library. It includes the NVIDIA Collective Communications Library, nicknamed NCCL, for high-performance multi-GPU performance scaling, a complete suite of dense and sparse linear algebra routines, which comprise the low-level building blocks for many deep learning algorithms, the TensorRT deep learning runtime for advanced neural network optimization and low latency runtime performance, and the DeepStream SDK for real-time AI video analytics. The Deep Learning SDK is performance optimized for all NVIDIA platforms, ranging from Titan GPUs and desktop systems to Tesla GPUs and DGX servers in high-performance data centers, to energy-efficient, low-powered embedded platforms such as NVIDIA Jetson and Drive platforms. And since this same SDK is supported across all NVIDIA platforms, developers can easily migrate from convenient development environments to production-class deployment platforms. Speaking of convenient environments for development and production deployment, NVIDIA GPU Cloud, NGC for short, provides data scientists and researchers with simple access to a comprehensive catalog of GPU-optimized software maintained by NVIDIA and others. NGC containers are optimized, tested, and certified for all the deep learning frameworks and many high-performance computing, or HPC, applications. So you can have confidence you're taking full advantage of NVIDIA GPU acceleration. Using NGC containers, you can get your environment set up in minutes and have confidence that the same environment will be used for both development and deployment, whether you're using on-premise data center, cloud service providers, or a hybrid of both. As AI is increasingly deployed at scale in factories, stores, city streets, and healthcare facilities, many organizations need the ability to securely deploy and manage complex software solutions across thousands of IoT sensors, edge systems, and servers in the data center. NVIDIA EGX addresses this need with its cloud-native, edge-first, scalable software stack, which includes support for NGC containers and Kubernetes-ready Helm charts that make it easy to deploy powerful AI software at scale and build customized solutions. EGX enables IT to quickly and easily provision GPU servers using GPU operators, which standardize and automate the deployment of all the necessary components for provisioning large-scale GPU-accelerated solutions. There are a wide range of GPU-accelerated platforms you can use to accelerate deep learning training and inference application workloads. In the data center, the Tesla V100 with NVLink technology delivers strong scaling support for mixed workloads across both HPC applications and deep learning training and inference applications. And for scale-out inference workloads, the Tesla T4 GPUs support high efficiency, low latency performance. GPU-accelerated servers are available from every major OEM and cloud service provider. If you want a fully integrated solution, we recommend the DGX computers in a box. Actually, let me say that again because that was just a mistake. If you want a fully integrated solution, we recommend the DGX supercomputer in a box, which deliver the performance equivalent of hundreds of CPU-only servers using 8 or 16 world-class Tesla V100 GPUs, or their little brother, the DGX Station, which is powered by 4 Tesla V100 GPUs and runs whisper quiet next to your desk. That's better. If you just want to get started on a prototype using your existing workstation, the Titan desktop GPUs also include Tensor cores designed specifically for learning that deliver up to 12x higher peak teraflops for training. As you would expect, NGC containers can be used across these desktop and server environments, so you have a seamless deployment path to production in the cloud or in your own data center. And, of course, if you need to deploy deep learning applications in automotive, robotics, or embedded applications, NVIDIA offers the Drive AGX and Jetson AGX platforms. So, in summary, to address these challenges, NVIDIA delivers training and tools for a new generation of data scientists and developers via practical, hands-on training from the Deep Learning Institute, a global series of GPU technology conferences, and easy-to-use deep learning workflow tools. The Deep Learning SDK, which is frequently updated with new and optimized algorithms and supported by all the major open-source deep learning frameworks. High-performance deep neural network training solutions that you can use in the cloud, data center, and workstation environments, and a wide range of deployment platforms with software and hardware optimized for deep learning inference in the cloud and data center, as well as automotive and other embedded applications. Now that you are ready to get started applying these deep learning approaches in your own projects, the first step is always to get clarity on exactly what problem you need to solve. Consider whether the expected results of this project are worth the effort in terms of market opportunity, benefit to humanity, or other factors, and whether there might be an easier way to accomplish the same results. If you decide to apply deep learning, you'll need to determine which AI tasks are involved. It could be detection, classification, segmentation, prediction, recommendation, or a combination of several tasks that implement a more complex solution like speech to text to text, and text to another language, and then text back to speech. As part of this, be sure to assess what level of accuracy is required for success, including fault tolerance, since every statistical method fails in some situations. You'll realize quickly that the accuracy requirements for an autonomous vehicle that will drive millions of people to work every day are very different than a product recommendation service. As the famous statistician George Box once said, all models are wrong, but some are useful. So think in terms of guardrails and heuristics will allow your application to know when something has gone wrong. Basically, all the standard good programming practice that your application should be doing with or without deep learning. The next step is to assemble the data set you will use to train the deep neural network. You may already have the data you need standing by and ready to be used, or you may need to invest some effort in collecting and labeling enough examples to create a representative data set. There are some great open source and commercial data sets online, but if you can't find what you need, you may need to apply some creativity and generate it yourself. Deciding which framework and tools to use depends on a number of factors, including whether you prefer a graphical workflow, a command line interface, or a programming language interface, which programming language you want to use. When you're first getting started, it's a good idea to try some small projects with different frameworks to evaluate which one you really want to learn well. Similarly, there are several factors that will influence which platforms you use to train and deploy your deep neural networks. These include important considerations such as where you have convenient access to high-performance computing resources and where your data is stored, since moving large amounts of data can take a long time. The good news is that all of the leading deep learning frameworks have built-in support for GPU acceleration, and all of the major server vendors and cloud service providers offer GPU-accelerated servers. So you have the flexibility to choose a solution that meets your needs with confidence that you will have access to the parallel computing horsepower required by deep learning. So what's next? Learn more about hundreds of AI applications at the Developer News Center. Listen to startup founders and researchers describe their work in the NVIDIA AI podcast. Practice building your own deep learning applications with the Deep Learning Institute, and join us for a GPU technology conference near you. Thank you for joining me for this introduction to deep learning and accelerated data science. And so with that, I'd like to thank you again for making time to learn about deep learning and all the great questions you've shared with us via the chat console. It looks like we have a few minutes left, so I'm going to look for some questions that haven't been answered yet and pick a few to answer live. And while I'm doing that, if you haven't already registered for GTC, please visit the website to learn more. I hope you'll decide to join us for the conference this March. And please feel free to use my NVWRAMI registration code to save 25% on registration. Let's look at some of the questions here. So the question here from Josh, who asks, as an expert in data science and AI, when do you suspect self-driving cars will see mass implementation? Well, Josh, thank you for characterizing me as an expert. I think I still have a lot to learn, both in data science and AI. But from the progress that I'm seeing, self-driving cars there's several levels of self-driving cars. And some of the early models are already on the roads today. While I don't own one myself, many of my colleagues here at NVIDIA have cars that, once they're on the freeway, will drive them through their daily commute to work and home again with little to no interference from the driver. And this allows them to enjoy the ride and our traffic here much more than they would if they had to do it all themselves. But I think for a fully autonomous conversion, that it's more than just the technology. It's going to require both a level of acceptance from the general public and an exploration into what the rules of the road and the regulations will be as this new technology becomes more prevalent on the road. So I think we probably still have several years to go before we start to see cities and regions adopting primarily self-driving cars, and probably much longer than that before we feel like self-driving is the new normal. But thank you for the question. I think we're all eager to see that future come to pass and have more flexibility in how we spend our time while transporting ourselves from place to place. Let's see. Here's a question from Silton Collymore. In fact, I recognize Silton. We recently connected on LinkedIn. Thank you for joining us today. His question is, do you support startups who want to use your devices in their solutions? And the answer is absolutely yes. We have a variety of ways that we can help startups. Most of them through the Inception program that we talked about earlier. And I'd encourage you to apply for that program if you haven't already, and take advantage of things like introductions to potential sources of funding, introductions to potential customers. There are some discounts available to members of the program on hard-hand access to, through our partnership with AWS, large numbers of GPU servers in the cloud. We also, for startups who have progressed to a certain point, like to help them with some technical advice and reviews of their plans. So I'd really encourage you and anyone else who is working in a startup to join our Inception program and take advantage of those benefits. Next is a question from Christopher. And his question is, how will the European Union's ethics guidelines for trustworthy AI change the artificial intelligence and machine learning development? You know, that's a really good question. I think a lot of us are reading those guidelines very carefully and trying to understand both the guidelines and the intent behind them. AI is a really powerful new technology, and I think it's incumbent upon all of us to be very thoughtful about how we invest our energies in advancing the technology and in what use cases it should be applied. I don't have an exact answer for your question, other than to, I think, echo your sentiment that it's a really important area for all of us to be cognizant of and recognize that just like any other technology, it's a basic capability. And we as individuals and as organizations really need to be thoughtful about how we apply that capability in the world. Here's a question from Gary. Gary asks, are TensorFlow and deep learning frameworks optimized to run on NVIDIA GPUs? And how do I get the GPU versions of TensorFlow and other libraries? Well, that's two questions, but we'll give you a two for here, Gary. The answer to the first question is yes, of course. All of the major deep learning frameworks are optimized to run on NVIDIA GPUs. And the answer to your second question is there are several ways that you can get access to the best GPU acceleration in those frameworks. Here at NVIDIA, we're constantly working on these frameworks. We have dedicated engineers working on each of the major frameworks and are implementing the latest algorithms, improving the performance, doing additional testing and validation that we package up into containers that are available via our NGC container repository. And containers make it really easy for you just to pull the container down and run it. All of the dependencies and build instructions and everything else has already been sorted for you there. So that's a really easy, quick way to get started. And also to ensure that your entire development team and even your deployment environment has a configuration that exactly matches, which can be a big problem if things get out of sync. But if you're pulling open source frameworks directly from GitHub or other locations, we are constantly contributing and issuing pull requests for our changes to get them upstreamed and integrated into the baseline repositories as well. So lots of ways to get GPU acceleration, but I would recommend as a starting point that you go to the ngc.nvidia.com site and pull down a highly optimized, pre-tested version of the container to get started. Next question is from Mirdad in Florida, who asks, how do you see the future of this area? The number of applications are drastically increasing, but I don't know if the industry has the same pace. You know, that's a really interesting observation. I think that there are some industry segments where deep learning is being adopted very rapidly, particularly in areas like manufacturing, where you can use deep learning to very effectively optimize your supply chain and logistics, as well as improving some in-store or online experience through, let's say, more capable recommendations and other services. We're even seeing some gradual adoption in industry segments like agriculture, where I believe it was last year, a startup named Blue River Technologies had developed a really cool technology that allows them to optimize the yield of lettuce crops while minimizing the use of pesticides and fertilizers. Really, really great technology that they created. And they're now looking at how do they apply that at crops beyond lettuce. And they were acquired last year by John Deere. So seeing the amazing innovative work that startups are doing, and then in many cases being acquired by larger companies who can make significant investments to help them scale and expand that technology across an entire industry is I think, promising. Next question is from Randall in Texas. Randall asks, how is NVIDIA promoting machine learning, deep learning, AI among general scientific researchers, for example, attending specialized conferences? Well, you know, that's a great question, because there are so many opportunities where AI can be applied in so many different fields of research as well as industry segments. where it can make a big difference. We do attend some specialized conferences. We also invite people from all different research and industry areas to attend our GPU Technology Conference, or GTC, conferences that happen all over the world. We also engaged with academic researchers by supporting their research, promoting their papers, doing say researcher or developer profiles that talk about the work that they're doing to help spread that knowledge. And particularly for researchers who are either funded by or doing work at some of the large supercomputing centers, we often work with some of the user services teams and others to help them accelerate their applications and learn how to apply best practices across all of the workloads that are running at those facilities. So lots and lots of opportunities, and we are trying to on those that are the most effective. But if you are interested in learning more about that, Randall, I'd encourage you to reach out and contact me via LinkedIn, or check out our developer.nvidia.com website that has more information on our higher ed and research programs. Thank you for asking the question. Let's see, Dharmesh is asking the next question. It says, is there any application for NVIDIA GPU in environmental research? In fact, yes. Even before the big bang of artificial intelligence, NVIDIA GPUs were being used to accelerate some of the largest weather and climate simulation applications in the world. For example, for the simulation application, you would see some examples of the performance benefits and results that NVIDIA GPUs are able to accomplish for weather forecasting and climate research. And also, you know, one of the things that would be a great resource for you, Dharmesh, would be to go to the GTC archives. Many of the session, the research presentations and other materials from previous GPU technology conferences are available to members of our developer program. So if you go and log in, you can search through all of the archives for keywords like weather, climate, environmental, WRF, and so forth, and find a significant number of really great resources there that talk about how GPU acceleration is having an impact on that entire field of research. Wow, the questions are coming in faster now. This is great, guys. Let me just look through a couple of these and pick the next one. So Lori asks, as a product marketer who has past experience with tangible products, what education or research would you recommend to begin transitioning into this type of intangible product? Well, Lori, I think as a product marketer, attending a webinar like this is a great first step. I would also recommend listening to episodes from the NVIDIA AI podcast. If you just search for NVIDIA AI podcast online, you'll find it. In fact, I was interviewed on the podcast and later had the opportunity to be the host and interview some guests on the podcast. And we have a lot of fun over there. So I would recommend that that's a great place for you to get some good information about use cases and how people are talking about the benefits of AI. And that'll put you in the right direction and give you a lot of references and links to additional resources that you can pursue to further your education. Here is the good question from Will. not me, but another Will, who asks, what are the uses for deep learning in the data center? Well, any application that benefits from GPU acceleration can run in the data center. So that's one example, and there are hundreds of those. We actually have a GPU accelerated applications catalog that lists several hundred really powerful GPU accelerated applications that are already available in the world. We only list the widely used applications in the catalog, but I'd recommend taking a look at those. In terms of actually running and managing a data center, there have been some really interesting projects, I think first published by Google in their own data centers, but since replicated and applied in many others, where they've been able to use deep learning to predict utilization trends and spin up and spin down hardware resources. And through that optimization, save a significant percentage of their operational costs. And by reducing that total cost of ownership, less on electricity and heating, rather not heating, but cooling systems, have been able to save a tremendous amount of money, which then gives them the flexibility to either reinvest in more powerful and more efficient computing systems, or pass that savings through to the bottom line or invest in other parts of their business. There are other uses for deep learning in the data center that have come out that are described more in our high performance computing section of our website at nvidia.com. So if you go to www.nvidia.com/HPC, then you'll see more examples there. Thank you. That's a great question. Next question. I think we have time for one or two more. Next question is from Aditya in Georgia. Aditya asks, as a college student, how would you advise, or what resources could we check out to dive further into the field and be able to work on applications of deep learning technology sooner? Well, Aditya, I think the fastest way to jumpstart your education and experience with deep learning is to just dive right in and get some hands-on experience. The easiest way I know how to do that is through our Deep Learning Institute. And you can do that just by going to nvidia.com/DLI. That'll give you a list of all of our self-paced online courses. And you can sign up and access those and get step-by-step instructions as you walk through the process of managing your data set, selecting and training a deep neural network to perform various tasks, and then actually optimizing and testing it depending on the course that you sign up for. There are fairly short 2 to 3 hour courses as well as full day courses, so you can decide how much time you want to spend on each topic. In addition to that, I would encourage any professors or teachers to check out the deep learning teaching kits that are available from NVIDIA. These are semester-length courses, or rather materials to support a semester-length course that can either be used in whole or just by selecting the modules that you need to fill in gaps or introductory segments in a course that you're already teaching. It includes all of the slides and instructor notes, as well as lab assignments, tests, and answers to the tests and the assignments for the professors to use in grading. Because it includes the answers, these materials are, of course, only available to qualified instructors, teachers, and professors. But you can apply for all of that for free on our website at developer.nvidia.com, or just search for teaching kits. Great question. Thank you. Let's see. Last question. This is a great question from Bart in Louvain. He's asking, what happened to GTC in Europe? So we have had a GPU Technology Conference, or GTCs, in many cities around the world. And we don't have it in every city every year, but we're working on the schedule for the rest of this year and the early part of next year. And we do have a plan to include a GTC Europe again in the near future. So stay tuned for more updates on that. And in the meantime, please continue to join webinars like this one. And if you can, please come and join us for the GTC in Silicon Valley. It's the first, the largest, in many ways the best, even though it is far away from many people. But we're expecting on the order of 10,000 people this year for a full 5 days of the conference. It's just going to be an amazing experience and opportunity for you to meet people from many different industries and fields of research and connect with them one-on-one while you're here. So with that, thank you again very much for joining us today. We really appreciate your time and look forward to seeing you again in the near future.
Thank you for attending our webinar. We hope you found it interesting and informative. As a reminder, an on-demand version of the webcast, as well as associated resources mentioned earlier, will be sent out in approximately 1 hour. Thank you and have a great rest of your day.